Hi, my name is Byungji and I'm a developer of CodeChain team. Today I'm going to talk about how we adopted BLS signature aggregation to CodeChain Foundry. These slides I'll talk about mainly first what is BLS signature and why we want them and how we adopted them into Foundry and some benefits and concerns on our new scheme. First, I'll give a brief introduction to BLS, what is BLS signature and why we need them in CodeChain Foundry. First, BLS signature is a promising digital signature scheme which allows aggregation of multiple signatures. It is suggested by these three cryptographists, and simply BLS makes use of two elliptic curve groups G1 and G2 and a bilinear pairing function E, which means that E is a function from G1 cross G2 to G, where it satisfies the following property, which means that the multiplication in the G1 side is equivalent to the multiplication in the G2 side in the pairing function. So let's assume that the private key is X. Then the public key is given as the G multiplied by X, where G is a generator in the group G1. Signing can be done by just multiplying the hash of the message by X. Then verification can be just simply done by checking this formula, because this is equivalent to EG multiplied by X and this hash and EG and hash of multiplied by the X, and we already said this property. So the main point, the most important point, is that BLS signature allows signature aggregation, and moreover it allows signature aggregation non-interactively, which means that the signers doesn't have to cooperate to aggregate the signatures. So signature aggregation can be done by anyone. And also it can be done without predetermining the number of signers at the signing step. And I want to say about this because actually Foundry introduced Snore signature, which also allows signature aggregation, but we failed to aggregate the signatures in the consensus step because Snore signature required to predetermine the number of signers at the signing step and use the information when signing. But actually, we don't know how many signers will sign at the signing step in Tendermint consensus. So this is how signature aggregation works. When there are multiple signatures, let's say sig1 to sig_n, then the aggregated signature is just simply sig1 plus sig2 plus sig_n, where just addition is under the group operation. And verification is very straightforward. First, we aggregate the public keys in the other group side, and we just do the ordinary signature verification of the aggregated signature with respect to the aggregated public key. This works because this formula is equivalent to this. And why do we want the BL scheme? Because we want to reduce the signature of the block header. And Tendermint consensus engine, it requires multiple signatures in the block header because each validator signs a commit message to express its consent to the commit, which means that to agree on the commit message, then it has to sign on the message, and the proposer has to append the signatures on the next block header to prove that the previous commit was valid. Therefore, in each block, in the header, it has up to the number of validators, the signatures, as many as the number of validators. Currently, Foundry mainnet has 30 validators, so it requires 30 signatures in each block header, but this may increase in the future, maybe about to 100 or 300. But anyway, if we use signature aggregation, the signature in the block header can be reduced from 30 signatures into a single aggregated signature. And that's the main reason we want to adapt BLS signature aggregation in Foundry. So I'm going to talk about the slight detail of our implementation and how we implemented this BLS signature in Foundry. So first we chose the BLS 12381 implementation, which this specification. This is specifies which group and which pairing function we're going to use, and it is known that it provides about 128-bit level of security, so it is quite popular among BLS specifications. And we use for now we use Algorand's Rust implementation of BLS 12381 because it is one of the reference implementation of the BLS signatures draft standard, and which is given by some cryptographist who wants to standardize the BLS signature scheme. And please note that this is still work in progress, so we don't it is not perfectly secure for now, but actually we can always change this implementation as long as the new implementation is based on the BLS signature standard. Also, I want to mention that there were two available options because, as I mentioned, BLS signature makes use of two elliptic curve groups, G1 and G2, and they are interchangeable. So which means that we can, first option is using G1 as a signature and G2 as a public key. And the second option is using G1 as a public key and G2 as a signature, but one was dropped due to performance reason of this Algorand implementation. I mean, this is not an inherent property of BLS, but it was a problem of the hashing function. So for now, I'm not going to consider one of it, and I'm just use the only one. In the case that each signature is 48 bytes long and its public key is 96 bytes long. Please note that in Schnorr signature that we previously used, the signature was 64 bytes long. So this is some of our implementation detail. We decided to use two different signing schemes for block header signing and transaction signing. So we use ED25519 signature for transactions and use BLS signatures for tendermint consensus messages. The main reason behind this is that BLS is quite slower than the transactions, slower than the other ED25519 signatures. So we thought it was not worth to use BLS signatures for all transactions because it will slow down the blockchain system. And also, since we use different signing schemes for tendermint consensus, we cannot infer the BLS public key from some other information, so each validator has to present this BLS public key at the self-nomination step, at the registration step. To prevent row key attacks and replay attacks, we require validators to present the following signature. So row key attack means that a validator, a malicious user, tries to say that he owns a key pair even though he does not. So to prevent this, we require them to sign on their public key. So because they cannot sign without the private key. And to prevent replay attacks, which means that the row key, public key the registration message can be reused. So to prevent this, we concatenate the BLS public key with the address. So we can use some schemes to prevent replay attacks in transactions. So I'm going to talk about some benefits and concerns of BLS signature. I'll compare BLS signature with the Schnorr signature that we previously used. The main advantage of BLS signature is reduced storage use of block header. When there are 30 validators, we can reduce space to 1 to 40 because when we use Schnorr signature, we need 64 times 30, so 1920 bytes to store signatures in block header. But if we use BLS signature, we just need 48 bytes, which is the size of single BLS signature. When there are 300 validators, the gap will become widened. So with Schnorr signature, we need 19,200 bytes, but with BLS signature, we just still need only 48 bytes. So this is a great advantage. But the main concern on adapting the BLS scheme is performance, because BLS signature verification is slower. BLS signature is slower to sign and verify compared to the Schnorr signature. We performed some benchmark on Schnorr and BLS signatures respectively, and we can see that the BLS is 8 times and about 60 times slower than sign and verify respectively. So this is one of our concern. And the slowed down signing and verification, slowed down the overall consensus process as well. So when I tested on my local laptop, and I checked the number of blocks which achieved a consensus in the first round, and the number of blocks moved to further rounds. So in the Schnorr signature, most of the blocks achieved consensus in the first round, but when I use the BLS scheme, there are some meaningful number of validators and meaningful number of blocks which move to further rounds. The block moved to further rounds means that it failed to make consensus in the first round, and because I tested on my local laptop, failure of the consensus directly implies the failure due to performance problem. So this is quite meaningful problem. It was just a test on my local laptop, so I expect it is not that significant. It won't that significant in real cases. Actually, BLS schemes provides faster header verification for non-validator nodes, although it slows down the consensus process. Because if you use Schnorr signatures, validators and even non-validator nodes have to verify signatures in block header one by one. So for example, if there are 30 validators, then they have to each node has to verify 30 signatures one by one. But if you use BLS signature scheme, then the verification of multiple signatures can be optimized. So the verification can be done as follows. First, nodes can create an aggregate public key from the set of public keys, and then they can verify the aggregated signature using the aggregated public key. Note that the cost of the public key aggregation is negligible, so the cost of verifying an aggregated BLS signature is almost same as the cost of verifying a single BLS signature. We performed a benchmark about this too. When we verified 30 aggregated signatures, it takes about this time in Schnorr signature, and BLS was about 1.8 times slower than this. But when the number of validators has grown to 300, then BLS becomes 6.4 times faster. Note that BLS, the verification time consumed by BLS even reduced, but this is just due to some precision problem, and because the time consumed by BLS is almost same. So this is the conclusion. If we adopt BLS signature aggregation, then we can get smaller header size and faster header verification. The disadvantage is slower consensus message handling of validators. But it is worth to say that it is worth to use this BLS scheme because the pros is the pros of all nodes, including non-validators, and cons, this is just for validators only. So non-validator nodes gain significant benefits from BLS signature aggregation. So to adapt BLS signature aggregation, we need further investigation on the impact of performance degradation, and we will continue investigating on this. So if you have any question, please ask to us CodeChain through GitHub or email. Thank you.